This is my final soldered and encased circuit for project 1.5, the counting circuit. It can turn off and on, count forwards and backwards, and even reset at the press of a button. So how does this circuit work? This diagram here shows how the clock signal for this circuit is created. The PNBO here, or push button normally open, is what controls the power in the circuit. When the button is not pushed, the NAND gate converts the high signal to a low. But when the button is pressed, the current goes straight to ground, creating low on both inputs of the NAND gate and outputting a high. The next part of this circuit is RC1. The capacitor charges almost instantly with the 9-volt power supply and then into the series of 3 NAND gates while being drained by the 1 mega ohm resistor. RC2 is what controls the frequency. The output of pin 11 goes to pin 1, which charges the 0.1 microfarad capacitor. This capacitor creates a high at pin 2, creating a low at pin 3. This creates low inputs and high outputs for the second NAND gate, and high inputs and a low output for the last NAND gate. Since there is a voltage drop between power and the low output of the last NAND gate, the LED lights up. The oscillation happens when the 0.1 microfarad capacitor finishes discharging and starts recharging. This creates a low output on the NAND gate outputting a high, which inputs a high outputting a low, which inputs a low outputting a high. And since the LED connected to ground is the same as the high output, the LED does not light up. At this point, you might be wondering how a digital chip reads an analog input. It's actually fairly simple. All the chip does is see anything below half the voltage at low and anything above that as high. But back to the circuit. We now need to send the output into a decade counter, which will divide the frequency by 10. Just send the output into clock and then take your input from the divide by 10 lead. The way the decade counter divides by 10 is by waiting until 10 clock signals have come by to output a signal itself. The current then goes into a 4510 where the chip counts the frequency and translates it into 4-bit binary code. Wiring this in creates a working binary counter. To change the frequency counter from binary code to something we can read, we will be using the 4511 chip. All you need to do is wire in the binary value of 1 to A, of 2 to B, of 4 to C, and of 8 to D. All you need to do to connect this to the 7-segment display now is connect the outputs of the 4511 A to G to the inputs of the 7-segment display A to G. This should give you a final working breadboard prototype of the counting circuit. Now, all that's left to do is to put the circuit in a PCB and in a case. Thank you for watching my video. I hope you learned a thing or two about the counting circuit. Thank you very much and have a good day.